Hello and welcome to another edition of the EWI Technology Podcast. My name is Max Saron and I am here in Columbus, Ohio at the EWI headquarters where we have been interviewing some of the great talent they have here in the building. We've been tackling topics from polymers to robots to all the fantastic science that happens in this building. And today, right now, we have Miranda Marcus who's going to talk to us about, well, a number of things, polymers, HACS, all these things I've been reading about, and you're a senior engineer here. Miranda, how are you doing?
I'm doing pretty fantastic. How are you?
Good. Did you like that introduction?
Yeah, it was very snazzy.
Thank you. So, Miranda, how long have you been working here at EWI?
I've been here 11 years.
11 years. I have never lasted anywhere 11 years. Maybe I shouldn't say that. But...
Well, now this is your chance. This is the one that's going to stay.
This is the sticking point, right? Yeah. And how did you get into EWI? What was it that brought you in here?
Well, I was working at an equipment supplier in Chicago area.
Mm-hmm.
And EWI had a pretty large polymer group, and it gradually dwindled over the years. And their last person left, and they were struggling to find anyone who was a specialist in plastic welding. And they offered me like a 40% raise to move back to Ohio and come here.
Well,
so I did.
That's pretty significant.
Yeah.
And I think Ohio is cheaper than Illinois to live anyways.
It sure is.
Yeah.
It was good all around. And this is where my family's from anyway, so.
Oh, that's fantastic. Yeah. What you said there was actually interesting. So it went from a large polymers group to almost none, and then revitalized into, bringing you in. And now it seems like it's quite big again, a team.
Yes.
What happened in that time frame that, before you, that it was big and kind of died?
So it was just a lot of natural attrition. So I think there was about 17 people in the group back in the 2000s. And then some people left, some people died, some people retired.
And then, no. But was it industry related? Do you think that there was maybe less focus? I mean, that was the first thing I thought of. Was like, maybe polymers were really popular in the 90s and then died out, or?
No, I don't think so. There has been a lack of polymer welding focused education. I think this is really the thing, is like, there's not a whole lot of people who focus on polymer welding in academia, and therefore getting people with this expertise into a research facility like EWI, where you really need to have that theoretical academic background, is difficult. So I got my PhD at the University of Akron, which is like ranked top for polymer engineering in the United States. They were ranked top in the world a couple years ago. Before I went back for my PhD, the last person who touched polymer welding, and I went back for my PhD in like 2020. Last person who touched polymer welding was in 1999.
Wow.
Yeah.
That's a huge gap that you wouldn't see a gap like that in alloy or steel welding. Right? Like you wouldn't see that type of a gap in academia, because that translates into a gap in product development and a gap in procedural development, all the other gaps that can stem from that, correct?
Yeah, and it's a topic I'm pretty passionate about, actually. Because the lack of plastic welding education results in so many poorly designed, not well considered products. And here we see a lot of them it's failed in the field. And it can be very dangerous, because as we're using more plastics, more and more of them are being used to replace metals for products that have higher requirements. And it's really important that the weld is done properly, and having that void in theoretical knowledge is something that I'm passionate about.
It's detrimental, really, to the industry. Even myself, I've been in the welding industry since I was 17. So 1993, I started welding. And that train of education has been all-encompassing. It's been my life. And along that journey, I have come across people who were in the plastic joining field, right? It has kind of always existed on some level. It's gotten more popular as we use more plastics. But when I hear you discuss it, I realize that there may have been a lack of scientific backing for some of the products that were getting released and going out, which then I look at now 25 years later, 30 years later, and we're having problems with the recycling of plastics, the rehabilitation of plastics, the breakdown of plastics in the environment. Are we 30 years behind the ball on this, that we should have been working on this like way sooner?
Absolutely.
Yeah.
But to your point, though, a lot of those issues we're having with recyclability and reuse of plastics are with one-time use polymers.
Okay, right.
So, and those aren't welded.
Yeah, those are designed for that.
Right. So that's another sort of, it's even just a cultural issue to discuss there, which is as we got materials that are so cheap and easy to produce, they become more disposable. Whereas previously, like
you'd have glass.
A plastic spoon will last as long as a metal spoon if you wash it. I mean, not as long, but it'll last a really long time.
Really long time.
You could be using it for 10 years.
Yeah.
But instead, we consider it disposable just because it's cheap.
Yeah, and I went camping last year, and I have a bougie friend. You know those bougie friends you invite camping, and they're weird. And he pulled out these recyclable plates, and he's like, "Oh, they're just garbage." I swear they were better quality than my ceramic plates at home. And I was like, "No, I washed them. I have them at home now." Like, I mean, why? Just because it says disposable on the box, I don't see how something so well constructed could be disposable. Right? It is like a cultural thing.
Yes, and personally, I feel like at some point we'll get to a point where the cost of actually mining from our trash will become viable.
Yeah.
And then that'll be like the way we deal with that in the future.
Yeah, I kind of think it's going to go that way. I've watched Wall-E a couple times, and I very much think that that's actually on point for quite a bit. So now, when we're talking about the polymers that you work with now, these are the ones that we're looking to replace metals and glasses and ceramics. These are going to be high tensile, high yield, strength materials, and also materials that are easy to mix with other materials. That's something I've been learning lots in the reading, that polymers, you can use them, and I shouldn't say easy, but you can use polymers to connect to steels, to glasses, to other items, which with metals is almost impossible, if not, it's very hard to do. Is that kind of the world that you live in?
So not exactly.
Yeah, okay.
So that is more of like using adhesive or mechanical joining,
like
which I get into
plastics,
sometimes. Yeah. So when you talk about adhesives, most of the adhesives we use are polymers. They're thermoset polymers. Sometimes they're thermoplastic polymers. Like your hot glue gun is just a thermoplastic polymer.
Yeah.
What I work with, though, is welding polymers to polymers, which is where we are actually getting chemical interactions.
Oh, okay.
So we're getting the polymer chains themselves to diffuse across the melt interface, entangle on the other side, and that's where the bond strength is coming from, as opposed to just like surface level covalent bonds or
capillary. Yeah. So when you're looking at welding polymers, and I think of steel, I think of grain structures, I think of diffusion, migration. Are all these elements within the plastic world for joining in a different way or on the same level? How does that work?
Many of those elements are there for plastics in a different way.
Okay.
So thermoplastic polymers can be divided essentially into two groups for their molecular structure. Some like crystalline polymers and amorphous polymers.
Okay.
Some like crystalline polymers have some crystalline areas. So they'll have crystalline structure and crystal growth, just like in your metals. But they also have amorphous areas. So they're not completely crystalline, which is why they're more flexible.
Okay.
Amorphous polymers really don't have any crystallinity in them, though. And then diffusion is definitely is definitely present in polymers. I think it's really interesting to me the way that diffusion theory for polymers came about. There is a man, Voyutsky, in the 1940s who was looking at rubber, and rubber is just a thermoset polymer, but it's partially cured. So there's some amorphous regions and some crystalline regions, and there's some cross-linked areas, and some of the polymer chains aren't cross-linked, and because it has a very low glass transition temperature, it's pretty mobile at room temperature.
Yeah.
So what he did is he cut a slice in the rubber and pressed it back together, and came back the next day and found that the slice was gone. The polymer
without
had healed
heat,
itself. Without heat.
Yeah.
And he theorized that what was happening is the polymer chains were just migrating across that interface. And that was the diffusion theory. And then later that's been built on. We now have a theory for how the polymer chains move, which is called reptation.
Okay.
Basically like reptiles.
Yeah,
so
they slither. Yeah.
Yeah. That's the idea.
Yeah.
So we have this like mathematical theory now behind how the polymers move, and we can relate that back to the weld strength that we're getting. So we can relate the theoretical reptation time to how much weld strength we actually get out of our part, which is pretty cool.
So the more a plastic can move, the less rigidity it would have?
Yes. Yes.
So I'm trying to put the two together, yeah. So, and then when you want to join polymers, they have to be, and I think, well, I shouldn't say have to be, but like we're going to get there, but in a perfect world, you're taking two polymers that are exactly the same, then they'll have the same kind of attraction, the same diffusion ability, and at the end of the day, like any welds you'd want to be smooth and clean with no interference from one end to the other. Now, can that happen in plastics? Will it get to that bond is as strong, if not stronger, than the parent material?
You can get welds that are as strong as the parent material, absolutely. And we've even seen that with dissimilar polymers that we've welded together.
Yeah.
So where the bond between the dissimilar polymers is equal to the strength of the bond of the similar materials.
Okay.
And we have like similar to similar welds that are as strong as base material. Mostly where we lose strength in polymer welds is at stress concentration regions, at the edge of the flash zone. If the flash doesn't wet out completely through the weld joint, it leaves like a stress concentration notch. And then that can create cracking, especially along the interface between the heat affected zone where the microstructures change due to the weld and the bulk.
Right.
And just like in metals, if you want to get rid of that, you can go back and anneal it.
Reheat it, yeah. Now, in terms of the, this grain structure that you speak of, microscope, under a microscope, if I look at a polymer, the way it's built or cast, does that create the grain? If you're making a plastic and you're extruding it, is that part of the grain creation, like how it is in steel? Or is it something more within the chemical composition of the polymer that tells it what the grain's going to be like, or its internal structure?
Yeah. So first of all, we don't call it grain in polymers.
Okay. It's what's it called?
The crystalline structure would typically be referred to as spherulites.
Okay.
So the shape and size of the spherulites is dependent on the crystalline rate growth and thermal history of the polymer.
Okay.
The rate growth is inherent to the type of plastic it is. So the way that the spherulites are growing is based on the type of material.
Like harder, softer, thicker, thinner?
Yeah.
Or just chemical composition?
No, so the polymer chains themselves will have different sizes.
Okay.
And the different sizes that they are and the shape that they are affects how crystalline they can form.
Oh, okay.
So like your basic polymer is polyethylene. It just is a carbon backbone with hydrogens on both sides. It's very simple and it can crystallize very well. It can be very tightly packed. And it doesn't always get tightly packed. It depends on the grade, like the molecular weight of the polyethylene and its thermal history. But then if you do like a little bit of a change in the monomer group, which is 2 carbons with 4 hydrogens, if you take off one of those hydrogens and put on a different, what's called side group, so replace one of them with like another carbon and 3 hydrogens, then you have polypropylene.
Okay, gets a little bit more complex.
A little bit more complex. And then the polypropylene, if that side group is all on one side, or if they're on opposite sides, or if they alternate evenly, it can affect how they crystallize. And then that placement is referred to as either isotactic, atactic, or syndiotactic. and affects, the
Either a
material
piece, a
property.
part, or all, right? So now these structures, how are they set in the plastic? Is it during the cooling period after being produced?
Yes. It's absolutely, your crystalline structures form during cooling, just like in metals.
Yeah.
And as depending on the way that the polymers are molded, if they're extruded, if they're injection molded, the way that the crystallinity is formed, or if it's an amorphous polymer, the polymer chain orientation will be different. And when we go and evaluate the parts, sometimes we can see where there's changes in the crystallinity or chain orientation, especially in injection molding. You'll have different structure like on the edge of the injection mold, which is called a skin layer versus the bulk.
Where it gets compressed against on the way out, right?
Well, and it cools at a different rate, too,
right? Okay,
because it's close to the tool.
Makes sense.
So we can identify that in a process we use here called HACS, which is for heated after cross section. And what we do is we take the part, cross section it just like normal, mount, grind, and polish down to where we're interested in. And then, whereas on a metal, if you're doing metallography, you would etch it with a chemical. We can't really do that on polymers. Instead, what we do is we apply a little bit of heat to the surface. The polymer chains that have been mechanically moved around during the polishing process have thermal recovery. So you can see where their thermal history is.
Kind of pull back, yeah.
Yep. And that is where we can see where the changes in microstructure are.
Kind of from where they left the void behind.
Right. Yeah. So we can see we can see like the difference between the bulk polymer in an injection molded part versus the skin layer. We can see where the weld has happened. We can see the edge of the heat affected zone. And what's really important for welding is that we can see whether or not the weld zone is continuous, whether or not it's a continuous microstructure, indicating that indeed we got polymer chains to diffuse across that joint.
And all the way through, yeah.
Yep. So they entangle. Or if they didn't, and then there's just essentially a line through the middle, which is a really fabulous thing to know about the weld. And this is the only process that's available to even check for intermolecular diffusion in the weld.
Well, that's what I was going to ask. Like in welding world, there's so many ways to test a weld. Many of them overlap in what they're testing, right? Whether it was mag particle, which wouldn't work for plastics unless you put iron filings in it somehow. I don't know. Yeah, there's an idea. I just created a polymer. No, it's probably done already. But then like phased array, would that work? Or ultrasound testing.
Ultrasonic testing typically doesn't work for plastics because the geometry that we're working with is so complex.
It won't sustain that wave, the sound wave.
Well, it's just difficult to identify which are voids and which is just like the geometry of the joint that is designed in.
So this is kind of one of the only ways post-production, post-weld, to be able to check. Now, what about thickness? Would you have to say if you have a 1-inch piece of plastic and you join it through welding on both sides, would you have to test both sides, or would you have to cut cross sections out every number of joints? How would that testing process be done?
Yeah, so we would cut out an area of the weld joint, and we could set up a testing schedule like for that, like with any other test method.
Yeah.
When we're talking about testing polymers and welds, I like to think of our testing methods as either quantitative or qualitative.
Okay.
So quantitative testing methods like tensile testing, leak testing, burst testing gives us a number output. And that number we can relate to the weld quality, and it gives us like a history of that weld quality over time. But if that number changes, we don't know why unless we follow up with a qualitative testing method.
Right.
So the HACS is a qualitative testing method where we can see, is there intermolecular diffusion? Are there voids? Is it misalignment? Are we having flash go unexpected ways? So it really helps to identify what's going on in the weld itself.
Now, some of the flaws that you find in welding, are they similar to some of the flaws or in welding metals? Are they similar to the flaws you find in plastics, like lack of fusion, voids, what's the other one I'm thinking of? The lamination, where they would separate somehow. Do these happen? Are these issues also in the plastics world?
Yeah,
Yeah.
absolutely. Add to that cracking.
Yeah, I guess you don't really think of plastic just cracking like that because you think of it as being flexible and malleable, but when you're getting to these serious plastics, they're quite hard, some of them.
Yeah, and also, when we're welding with plastic, sometimes we'll be compressing like an O-ring or something in order to add leak tight. And if we don't hold the melt under compression for long enough, that O-ring will actually push back on the weld.
Oh.
And like crack through the not fully solidified melt. And when I talk about for long enough for plastics, this is very short.
Yes, like
so,
milliseconds.
Like half a second.
Okay. Now, how far has this technology and these products come, since you got into this? You've loved this for your career now.
Yes.
Right? So when you started this in school to, what you're doing in the labs here, how much progression, how much advancements have we seen?
Yeah. So I started plastic welding about 20 years ago. The biggest advancement since then has been servos. So adding servo control to plastic welders has been pretty huge. It's not a new idea, but when it was first conceived of, probably like the 90s or 80s, servo motors were just too expensive to incorporate. But as the technology advanced, they were able to be cheap enough to put into plastic welders, and it has really revolutionized the quality of plastic welds that we can achieve, which then opens up the applications that we can use it for.
What about the regulatory bodies that exist? Are they involved with the plastics welding and the plastics joining, I guess, world?
To a some of an extent.
Yeah.
So the regulatory bodies that exist in the United States are fairly limited. The one that has put some work into at least standards has been AWS, the American Welding Society. So they've developed some standards for plastics welding. And there's also the Society of Plastics Engineers, who has a welding group.
Yeah.
But they've not developed any standards.
Yeah.
A lot of the standards that we might rely on come out of Germany.
Okay, yeah.
The DNS. So there's definitely room for more.
Yeah, because, we were talking about that earlier on another podcast with the EWI staff about once something becomes regulated, then it's all hands on deck because it has to happen now.
Yeah.
Right. And, we think, I feel like there's going to be a transition towards a lot more plastic products going forward of this style, right? We're looking at transmission of liquids and gases, storage of materials, things that have kind of always been done in the steel world that now we're looking at plastics to replace those things. But those steel items are so highly regulated, you'd feel that you'd want to have some high level of regulation as well for the standard version of a plastic version of it, right?
Absolutely. So in some industries, there's industry specific standards.
Okay.
But oftentimes they're not specifically geared towards the weld. It is like an overall product standard.
Okay.
So a lot of polymers are being used in medical fields, including internal devices. And the welds that we do there have to adhere to a much different type of quality than, for example, if we're welding a toy.
Right. Okay. Yeah.
Which is another thing that's welded out of plastic. But we also do a lot of welds in the automotive industry. We have internal engine components that are being welded, safety devices like seat belts. And then, as we evolve in the energy sector, there's a lot of welds that are being used for pipelines as well.
Right. And we're looking about, hydrogen is such an issue for pipelines. And then a lot of people are looking towards the plastics as a way to work with hydrogen and the capture of CO2 as well.
Yes. Yeah. So there's some standards for welding of pipelines, but it's a more old school traditional type of welding,
Yeah.
where it's basically extrusion welding, which is almost like the stick welding of the
You're
polymer
melting
welding.
plastic into a gap, yeah.
Right. Yes. And
Yeah.
so there's standards to qualify a plastic welder, like the person doing the welding.
Mm-hmm.
But as we get more advanced technologies, we can do a lot of these welds with more automated processes, and we're going to need a different level of standards to apply.
And now your HACS method is probably the gateway into that higher level of testing, because you can't really elevate a procedure until you have the instrumentation or the metrology to support it, right?
Yeah, I hadn't thought of it that way, but absolutely.
Right, because if you can't test it, how can you prove it, right?
Right.
Right. And when you're working with the HACS, does it work for all polymers, all dissimilar polymers, polymers to metals? Will it work kind of with any, situation?
Yes. Yes, it does. So it does work best with similar polymers.
Okay.
Because that's primarily the area we're going to see intermolecular diffusion occur. However, if we're doing dissimilar polymers or polymers to metal, we can still see like the extent of the heat affected zone. We can still look for voids and cracks and other things, but we're not going to see evidence of diffusion in those cases.
At least not on one side, or I guess on either side.
Well, the diffusion happens at the joint.
Right. Yeah.
Yeah.
Now, when will the plastic diffuse more into the harder material than the harder material into the plastic?
The diffusion will only happen if the polymers have a similar viscosity and if they're chemically compatible.
Okay.
So we won't see like polymers diffusion into metal. That doesn't happen.
Doesn't happen.
Most polymers aren't miscible with each other, so there wouldn't be any diffusion for most dissimilar polymer joints.
Mm-hmm.
Those are going to be more like adhesive type bonds, but we can use welding processes to create them.
And do you still see that entanglement at the same level with dissimilar polymers?
Not typically.
Not typically, yeah.
We've been doing some work lately on seeing if we can promote that diffusion in dissimilar polymers by matching viscosity. We have a piece of equipment here where we can heat up the different sides of the weld to different temperatures using hot plate or infrared, so we can match that melt with viscosity and then weld them together. Initially, we haven't seen in the HACS cross-section that we're actually getting intermolecular diffusion.
Okay.
But we have been getting like really good strength. When we match viscosity, we increase the strength of that bond by 3 times.
And are we talking tensile strength? Are we talking
Tensile strength,
okay.
Yes.
And what about side load or yield strengths, like for bending around edges, like a side load? Is it still the same strength?
We have not tested shear or bending moment on those yet. We've been focused on tensile.
Yeah. Yeah. Well, that is the standard that everyone starts at.
Yeah.
Now, the hardness of the material, even if it's similar, does that matter? If a plastic is a harder plastic or a softer plastic, do you use different procedures? You said it comes down to viscosity and, how chemically aligned they are. So theoretically, if you have soft or hard, as long as you got the right viscosity, right chemical alignment, they should bond well?
Yes. So there are some considerations you can take into depending on the rigidity of the polymer in terms of the welding process you use. So there's about a dozen different types of plastic welding processes that are being used in the industry right now. And some of them work well with soft materials and some of them don't.
Right. Okay.
For example, we can't do ultrasonic or vibration welding of softer polymers. With ultrasonic welding,
they'll just jiggle and not stick.
Well, they'll melt at the surface. Like the ultrasonic, the viscous or non-rigid part of the polymer doesn't transmit any mechanical motion, and it'll just melt right where the horn, which is the ultrasonic device, contacts the polymer. With vibration, it will just jiggle, and you'll get like chunks of material torn off.
I think I'm a soft polymer, So
we should jiggle you.
Yeah. Now, what about when you're looking at testing? I have this vision in my mind. So in the world of steel, if I take two plates and they're just normal, iron plates, say 44, and I lay them side by side and I weld them with a 7018 and everything's happy at 70,000 tensile, I can buff this whole plate up. I can introduce a little bit of heat, just a little bit to the whole plate, and my weld color will come out in my heat affected zone and the center and not on the outside. I will visibly be able to see, kind of like this, just with a little bit of heat, the crystalline structure will expose itself through color, right, on a weld. And almost all materials will do that. Doesn't matter if it's copper, brass, stainless. They have their own color depending on how they reflect on the crystalline structure. How did you figure that out, or how do people figure that out with plastics? How did someone say, you know what, let's just buff it up and heat it and see what happens? Like, how did that?
Yeah. So in my case, when I started at EWI, as I mentioned, all the polymer group was gone.
Yeah.
One of my first projects was doing cross sections, and I was working with one of the metallurgists who'd been here for quite a while. And we were looking at these cross sections, and I was like, I can't tell anything in here. And he looks at me, he's like, well, I remember like 5-10 years ago, they used to like run a hot air gun over these.
Mm-hmm.
I said, all right, well, let's give that a try. And it worked fantastically.
Yeah.
So this is apparently a technique that had been developed at EWI around like the 1999-2000 period when there was a large group.
Mm-hmm.
But it had never been published.
Right. It was more anecdotal, like you just do this and
right.
Cool, right?
Right.
Yeah.
So I took it from that running hot air gun across it to using a very controlled process. Right. We use an IR oven right now. We control the temperature exactly. We predict what temperature we'll need to use for the cross sections. And we can, treat batches of them consistently. Mm-hmm. So we went from that, we'll run a hot air gun across it, to something that's a much more controlled and stable process now.
Do you see a place for this type of testing in the field where, it will go along with the plastic welders, and it's, there will be an inspector that will have to come out and use, a version of what you do in the lab?
Yeah, absolutely. So already in the plastic welding industry, there is destructive testing that takes place. One of the common ways that's established in the industry is called microtoming, which takes a very thin slice of plastic. And doing that, you can see like the edge of the heat affected zone, but you can't see whether or not there's been intermolecular fusion in the weld joint, typically. So this is like a more advanced step of that type of quality inspection. Mm-hmm. And that absolutely is something that people can have in their lab, in their production facility, in order to measure the quality of the plastic welds over time.
Do you think this process could evolve into a non-destructive form of testing the plastic? No. You have to get, because I'm thinking of thickness. Like in a non-destructive format, you'll just see the surface, right?
Right. And
I'm throwing the hard questions out here.
If we're just looking at the top surface of the weld, we would not get a good idea for whether or not there's intermolecular diffusion. We have
voids or anything.
Yeah, voids and flash at the surface. I guess potentially you could grind down below the top surface in some areas. And so if that was acceptable, that might be something that you could do. It would not exactly be non-destructive, but it would be less destructive.
Yeah, just, I'm trying to think of that toolbox, down the road with science, because at the end of the day, the people out there that do the work, it's got to be done quick and on site and always with as little disruption as possible. And as we've talked about, there doesn't seem to have been the investment into the plastics world over the last 30 years that there probably deserve to have been. And so it's kind of like playing catch up, because when I started welding 30 years ago, the testing was a million years behind how the testing is now. the advances. Like I remember things having to get sent to labs in other cities, and you wait, weeks for things to come back, and now you can buy a $30,000 gun and go, and it tells you exactly molecular composition of that thing, right? I would love to see that in plastics. Do you see it kind of going that way eventually with the science?
There are some potential ways that we could do it. So one of the things that EWI has recently been exploring is called flash thermography.
Okay.
And this is not my area of specialty.
But sounds cool.
But it does, yes. So what it is taking a really bright light, flashing it at the part, enough to change the temperature by a degree or two, and then taking an infrared image
on the backside.
On the front side.
Okay, yeah.
Yeah, this is all a side test. And that will show you the thermal conductivity of the materials. And we've used that to identify like where the changes in material are. And we're still working to see how well we can use that to determine weld quality. But I think that's probably the most promising new evaluation method we're looking into.
It's almost like a sustained infrared test where it's like you heat it up and you see which part cools first because it's the dentist's part kind of thing.
Yes, but without actually
heating
the
it
part.
up. Yeah, without actually heating the part. That's super cool.
Yeah.
Now, what's next for you? You got these projects on the go. You got, your love for the plastics. What are you working on right now that's kind of like got you excited for the next steps?
Yeah, so the thing that excites me most right now is working with what I'd really love to get into, and I haven't had an opportunity to start doing this yet, is to see if we can use our equipment that we have different temperatures that we heat it to, so we can get different types of materials welded together. I want to modify that so that I can have sort of instantaneous measurement of the viscosity of the polymer and use that to adjust the heating temperature.
Okay.
So that I can weld together materials that have inconsistent material properties, which would be really useful for recycled polymers.
Yeah, because there's going to be an inconsistency in recycled. Yeah.
Yes. So I would. One of the things that I'm looking forward to doing in the future is seeing if there's a way that I can modify our equipment and this process.
Have a sensor there that monitors that edge, I guess.
Yeah, linear encoder is what I'm looking at.
You already got the shopping list ready.
I do. Yes.
And what about from industry? What are the types of industries that are coming to EWI to you and are asking for help in these processes and products? What is it? Is it mainly food production, like you said, or automotive, or who are the big players right now that are asking for help?
So at EWI, we work on the most stringent requirement applications, and that's a lot of medical.
Okay, yeah.
So we have a lot of work with the medical industry, diagnostic devices, surgical tools, implantables, fluid movement, test cartridges. We're doing a lot of that type of work.
And those are all plastics?
Yes.
And do you think that is there a movement away from metals to plastics in medical for a specific reason? Is it cost? Is it sustainability? What do you think it is?
There is a lot of interest in plastics and medical because it's cheaper and therefore disposable. So I did, as I was looking into plastics at one point, I read about, I forget the country in Africa. There's a country in Africa who, once they got polymer syringes instead of glass syringes, they eliminated hepatitis C, which cannot be killed by sterilization.
Right, because they would be using the same glass needle over and over and just putting them into autoclaves.
Right.
Right, and that's not enough.
Right, yeah.
Okay.
So that's a big advantage. If we can make the devices inexpensive enough, then they can be disposable, reduce contamination, and improve health.
Yeah, and also hopefully be able to have the post-use, industry set up to recycle those materials back into usable things.
After we, thoroughly.
You can ozonate them. I built an ozonator for a hospital once. I know that ozone kills everything.
Okay.
But there's like, I mean, it's very dangerous, but it's a neat process. Now, in terms of, the world's pressure for sustainability, green, energy savings, how much is the work you're doing trying to align with that?
Yeah, absolutely. So in many ways, that's a huge driver. And a lot of what we do is trying to find more efficient ways to bond things and reduce material consumption. One of the projects we worked on called Thin Seal, we were changing the welding process for form fill bags, like stack bags, for chips or other kinds of snacks that you might have. And we're able to eliminate, a quarter of an inch of film per bag because we can reduce the headspace. And when we're talking about the billions of these things made every year, that's a huge amount of
savings.
Savings of material. Reduced
consumption.
Yes.
And that's good because that's less than the landfills, because those are the kind of the one-time use plastics that are just going to go out.
Right.
Now, what about bioplastics? Like we've the world's been talking about bioplastics. I don't think we're very far into that world yet, but I feel like it's going to start to come. I've been at some conferences where they're talking about using, leftover eggs, wheat stalks, or rice leftovers to create bioplastics and biofuels. But one of the things that I've consistently heard is that those plastics don't react in the same way as some of the, common polymers that we use. Is that anywhere on your radar or anything like that?
I personally haven't done a lot of work with them, but I know people who have. So there's been a lot of interesting work from David Gruhl, who's a professor at South Dakota University. He used to be out of the University of Iowa, working with corn-based polymers, and now he's doing stuff with like welding of wood, which is really fascinating.
Oh, wow. Yeah.
Yes. So it's definitely something that's being worked on at this point more in the academic area than in industry.
It's good that it's getting done, though. Like you said, there was that gap in your life where it wasn't being done. And it's like we don't want those gaps in science to happen.
Right.
Because they filter down to society.
Yes.
You've been here 11 years at EWI. How's your team grown? You said you were kind of starting from scratch. What's the team look like now?
Yeah, so it started out, it was just me, and that was true for about 6 years.
Oh, wow. Just showing up for work with your lunchbox.
I had interns.
Yeah.
It was a little bit of a revolving door. I spent a lot of time teaching people what to do.
Okay, yeah.
But then I started out with one full-time, very talented technician, Matt Nitch. And from there, we gained a senior technology leader, Jeff Ellis, and then added another project engineer to our group, Jeff Boyce. So now we are 4 strong.
All right, right on. That's 400% growth. Well done. Well
Thank
done.
you.
Well, we're almost at the end of the interview here, but a couple questions. Number one, with the growth of your team, being able to take on more work, the advancements that you're seeing, what other avenues of testing have you guys been looking at, or is it all in on the HACS?
HACS is the best testing method there is. But we do all the different testing methods here. So in terms of weld quality, weld strength, we do a lot of leak testing. That's a really good non-destructive testing method for plastics, because there aren't a whole lot of non-destructive testing methods for plastics. But we also do burst testing, shear testing, fatigue, things like that. And we do a lot of just base material polymer characterization as well.
Well, and that's good because, the name on the sign says Edison Welding Institute. And I don't know if the average person or company out there in America knows that they could come here for those plastics things, right? And I think it's important to get the message out there that this is a leader in plastics technologies here. and that there are lots of companies could probably start looking for assistance or help from your group.
Yes, absolutely.
And the last question for you is, what would be the message that you would like the public to know about, your field, or the thing that might be maybe not construed well to the public, or maybe they don't know when it comes to plastics and its use in our world, and what your team is doing? What would be a great message you'd like people to know?
I think the biggest thing that I want people to know about plastics is they're not as dangerous as they're made out to be in the media.
Mm-hmm.
Plastics are inert. They don't actually affect your body. Things we hear about like BPA, that was additive used in some plastics. BPA is not a plastic.
It's not a plastic. Yeah, it's a coating.
Yeah. It's a plasticizer.
Mm-hmm.
So when people like worry about the amount of plastics in our world, it's almost like having more rocks. They're inert. They're not doing anything.
Yeah.
And we don't need to be as worried.
And we're working on it anyways. Like, we're trying to be more efficient.
Yes.
And we're trying to figure out how to work it out. So, because at the end of the day, waste is the issue. It's not use. Yes. Right? It's more about, like you said at the beginning, it's a cultural thing.
Yeah.
Because you can hold on to that plastic fork forever if you want to.
You really can. That's why we think it's a problem in the landfill, but it wouldn't be a problem in your house.
Right. That's right. That's a good way of putting it. Well, awesome. Thank you so much for being on the show. I've learned so much from you, and I really, really enjoyed this interview.
Thank you. It was very nice to be here.
Awesome. Well, thank you. And for all the people that have been following along these podcasts here at EWI, I hope you're learning as much as I am from these wonderful people. We have a few more coming out. Make sure you catch them all. You're going to want to. And if you have questions for us, shoot them in. Let us know. Email us, text us, or hit us up on Instagram. And we'll ask if, we love doing these recordings. And please stay tuned for the next episode.